A single radio signal once screamed across the cosmos with no explanation. Our universe is not the serene, predictable place we might hope. It is a theater of the bizarre, filled with phenomena that defy our very laws of physics and reality. By the end of this journey, you will witness 25 of the most profound cosmic anomalies that leave even the greatest scientists searching for answers. We will confront a void so vast it should not exist and a star whose light flickers as if something massive is passing in front of it. What cosmic mystery makes you question everything you think you know? That single screaming signal we mentioned has a name. It is known as the WOW signal, and it remains one of the most compelling mysteries in the history of astronomy. The story begins on a quiet August night in 1977. A massive radio telescope at Ohio State University, nicknamed the Big Ear, was methodically scanning the sky, listening for the faintest whispers from the cosmos. Its data was printed out on long sheets of paper, rows of letters and numbers representing the strength of any signal it found. Most of the time, the printout showed nothing but the gentle hiss of cosmic background noise, represented by a string of ones and twos. But on August 15th, something extraordinary happened. For 72 seconds, the telescope's receiver locked onto a signal so powerful, so precise, it defied all expectation. The intensity of the transmission spiked to a value 30 times louder than the silence of space around it. It was a narrowband signal, meaning it was focused on one specific frequency, just like a radio station tuning in clearly on your dial. This frequency, 1420 MHz, is a protected band in nature, a quiet channel where cosmic hydrogen emits a faint glow, a channel scientists have long speculated might be used for interstellar communication. The signal appeared, rose to a peak, and then faded away as the Earth's rotation moved the telescope's gaze away. When astronomer Jerry Amon reviewed the data printout days later, he was stunned. He circled the sequence of letters representing the signal's incredible strength, 6 characters reading 6EQUJ5. In the margin, overwhelmed by the discovery, he simply wrote one word in red pen: "Wow." That single handwritten exclamation gave the anomaly its famous name. In the decades since, astronomers have pointed every instrument they could at that same patch of sky near the constellation Sagittarius. They have listened for a repeat, for a pattern, for any hint of a follow-up. There has been nothing, not a whisper. The WOW signal was a one-time event, a cosmic shout that echoed once and then fell silent forever. This singularity is what makes it so haunting. Natural cosmic events like pulsars or stellar flares repeat. They have rhythms. This did not. It was a perfect, artificial-looking burst that has never been seen again. The debate rages on, a quiet tension in scientific circles. Could it have been a bizarre, never-before-seen natural phenomenon? A comet's reflection, perhaps, though that theory has serious flaws. Or was it exactly what it appeared to be, a fleeting, targeted transmission from an intelligence beyond our world? We may never know for certain, but that one red-inked word on a sheet of computer paper continues to echo through the decades, a permanent question mark written in the stars. That profound silence after the WOW signal leaves us staring into a seemingly random cosmos. But what if the universe is not random at all? What if everything, on the largest scales imaginable, is being pulled in one specific direction? This is the unsettling reality of dark flow. While the WOW signal was a fleeting shout, dark flow is a relentless, universe-wide current, a mystery written in the motion of thousands of galaxies. Scientists mapping the cosmic microwave background, the afterglow of the Big Bang, expected to see a calm and even distribution, a testament to a homogeneous universe. Instead, they found a strange drift, enormous clusters of galaxies, each containing thousands of billions of stars, are not just moving apart from the expansion of space. They are also streaming together like leaves caught in a vast, invisible river, all heading toward the same distant point on the cosmic map. This motion was detected by observing a subtle shadow effect, the kinetic Sunyaev-Zeldovich effect, where the hot gas in these galaxy clusters leaves a fingerprint on the ancient light of the cosmos as they rush through space. The speed is staggering, millions of miles per hour, and it points toward a region in the constellations Centaurus and Hydra, far beyond the edge of everything we can see. This presents a monumental problem. Our standard model of cosmology is built on the Copernican principle, the idea that there is no special place in the universe, that on large scales matter and energy are spread evenly. Dark flow shatters that assumption. It suggests there is a there, a gravitational anomaly so immense it can tug on entire superclusters from beyond the horizon of our observable universe. The leading theories to explain this are as mind-bending as the flow itself. One possibility is that a colossal, unseen mass, a structure of staggering proportions we simply cannot detect, lies in that direction, its gravity orchestrating this cosmic migration. An even more radical idea is that the pull is coming from something outside our universe entirely, a neighboring cosmos in a vast multiverse, exerting a gravitational influence through the fabric of reality itself. Dark flow is not just an anomaly, it is a challenge to our cosmic address, a hint that our universe might have a center, a preferred direction, and neighbors we can never directly see, only feel through their impossible distant pull. Dark flow reveals a universe tugged by unseen hands, but its pull points toward a specific and terrifying address. That destination is the Great Attractor, a monstrous gravitational anomaly lurking in the heart of our local universe. Think of it not as an object, but as a place, a focal point of such immense density that its gravity commands the motion of our entire galactic neighborhood. Our Milky Way, along with the neighboring Andromeda galaxy and every other galaxy in our local supercluster, is not drifting aimlessly. We are all falling at over 1 million miles per hour toward this invisible cosmic maelstrom. For decades, its true nature was obscured by a simple but profound obstacle, our own galaxy's thick band of stars, gas, and dust. This region, called the Zone of Avoidance, sits like a dense fog in the plane of the Milky Way, completely blocking our optical view of what lies beyond in the direction of the constellation Centaurus. It was as if the universe's most powerful magnet was hidden directly behind a blinding wall. The discovery came not from seeing it, but from feeling its pull. By meticulously mapping the velocities of thousands of galaxies, astronomers in the 1970s and 80s traced the streams of motion back to a single, powerful source. The Great Attractor had to possess the mass of tens of thousands of Milky Ways to exert such a force. But what was it? As observation techniques improved, allowing us to peer through the cosmic dust with infrared and radio eyes, a clearer picture emerged. The Great Attractor is not a single, unfathomable object. It is the core of our local supercluster, a colossal knot of galaxies known as the Norma Cluster, surrounded by an immense overlay of dark matter, the invisible scaffolding of the cosmos. This vast concentration of mass, both seen and unseen, creates the gravitational well we are sliding into. Yet the mystery only deepens from here. Recent, even more precise measurements have revealed something that reshapes the entire story. The Great Attractor itself is not stationary. It and everything it is pulling, including us, is also in motion. We are falling toward the Great Attractor, but the Great Attractor is being pulled toward something even larger and more distant, a titanic assembly of galaxies known as the Shapley supercluster. This creates a cosmic hierarchy of pulls, a Russian nesting doll of gravitational influence. Our local flow is just a small part of a far grander river, all streaming toward the most massive concentration of matter we have yet identified in the observable universe. So we are caught in a double cascade, swept first toward a hidden focal point, and then with that entire point toward a distant supercluster of almost unimaginable scale. This layered mystery forces us to confront how little we truly understand about the distribution of matter on the largest scales, and what other invisible giants might still be waiting, hidden behind the veil of our own sky. This grand cosmic river pulls us toward structures of unimaginable scale, but sometimes the greatest mysteries are found not in vast flows, but in the strange behavior of a single, distant point of light. Among the hundreds of thousands of stars monitored by the Kepler Space Telescope, one stood out as profoundly bizarre, a star now known as Tabby's star, or officially KIC 8462852. Its normal flicker of brightness caused by orbiting planets was replaced by something utterly erratic. Instead of the gentle, periodic dimming of a planet transit, this star would suddenly lose up to 22% of its light, an immense drop, and then just as strangely brighten again. The dips were irregular, asymmetric, and deep, as if something colossal and jagged was passing in front of it. The most famous theory, and the one that captured the public imagination, was the idea of an alien megastructure, a vast swarm of solar collectors known as a Dyson sphere under construction, partially blocking the star's light. While captivating, scientists sought natural explanations. The leading candidate is dust, but not ordinary dust. The star's dimming patterns across different colors of light suggest it is caused by clouds of extremely fine, microscopic dust particles, likely expelled by a disintegrating planet or a swarm of icy comets breaking apart. The latest observations show the dimming is more pronounced in blue light than in red, which is a classic signature of small particles as they scatter blue light more effectively. While the alien megastructure hypothesis has largely fallen out of favor, the natural explanations are still not fully conclusive. What could create such immense, irregular clouds? The mystery of Tabby's star endures as a testament to how a single anomaly can challenge our catalogue of stellar behavior and remind us that even familiar suns can hold profound, unexpected secrets. While Tabby's star hides its secrets in erratic dimming, another celestial object displays its mystery with breathtaking geometric clarity. Gaze upon the Red Rectangle Nebula, a structure that looks less like a cosmic cloud and more like a carefully drawn technical diagram. Located about 2,300 light-years away, this nebula surrounding a dying binary star system is one of the most symmetrical objects ever discovered in space. Through powerful telescopes, it appears as a near-perfect rectangle of glowing red gas with a startling X-shaped pattern of rungs like a celestial ladder spanning its core. This is not an illusion of perspective, it is its true three-dimensional shape. How does nature, which tends towards spheres and spirals, create such a precise geometric form? The leading explanation involves a dense disk of dust and gas ejected by the aging central stars. Imagine two stars orbiting each other, spinning like a top and blowing out dense stellar winds. If a thick torus or donut of dust encircles them, the winds from the poles can escape more easily, shooting out above and below to form two cone-shaped outflows. From our vantage point, looking at this system nearly edge-on, the edges of those cones create the illusion of a rectangle, and the rungs of the X may be caused by episodes of pulsed ejections from the stars, creating rings within the outflow that we see as crossbeams. Yet, even this elegant model does not fully explain the razor-sharp corners and the astonishing symmetry of the structure. No other nebula we have found looks quite like it. The red rectangle stands alone, a cosmic sculpture of impossible geometry, challenging our understanding of how stars die and sculpt their surroundings into forms that seem more born of intelligence than of chaotic physics. These strange geometric shapes are confined to distant stars, but our own galactic home hides a pair of colossal, invisible structures. Emanating from the very heart of the Milky Way are the Fermi bubbles, two vast lobes of searing energy that balloon outward, stretching halfway to the edge of our galaxy. They were discovered not by seeing visible light, but by sensing the universe's most violent radiation, gamma rays. The Fermi Gamma Ray Space Telescope, mapping the sky in these high-energy photons, revealed a startling silhouette. Two enormous, symmetrical spheres of gamma-ray emission were protruding from the galactic center, one north and one south of the dense plane of stars, together forming a shape like a colossal hourglass or an immense cosmic figure 8. Their scale is almost incomprehensible. Each bubble stretches 25,000 light-years from its base, meaning the entire structure spans 50,000 light-years. To put that in perspective, if you could see these bubbles in the night sky, they would cover an area stretching from the constellation Virgo all the way to Grus, the crane. They are a permanent, though invisible, fixture of our celestial landscape. The leading hypothesis points to a dramatic past eruption from the sleeping giant at our galaxy's core, the supermassive black hole known as Sagittarius, a star. While it is quiet today, astronomers theorize that several million years ago, it experienced a cataclysmic feeding frenzy. As enormous amounts of gas and dust spiraled into its event horizon, the black hole may have violently belched out twin jets of accelerated particles and radiation from its poles. These jets, plowing into the halo of gas surrounding the Milky Way, would have inflated these gigantic, bubble-like shock waves which still glow with gamma rays today. Yet this elegant story is filled with troubling gaps. The precise timing of this eruption is unknown, with estimates ranging from 2 to 4 million years ago. The energy required is staggering, equivalent to the simultaneous explosion of 100,000 supernovae, and we do not fully understand how the black hole could have channeled such power so symmetrically. Furthermore, the bubbles have remarkably sharp edges like the surface of a soap bubble, which is difficult for shock wave models to explain. Could it have been a single, monstrous burp or a series of smaller outbursts over eons? Was the energy driven by the black hole's jets or by a frenzied period of star formation at the galactic center? The Fermi bubbles are a ghostly monument to a violent event we just missed witnessing, a permanent scar on our galaxy that whispers of a time when the calm center of our Milky Way was a place of unimaginable cosmic fury. The violent history written in the Fermi bubbles speaks to a chaotic past, but the oldest light in the universe tells a story that is strangely, unsettlingly orderly. This brings us to one of the most controversial and profoundly named anomalies in all of cosmology, the axis of evil. This is not a dramatic nickname for a cosmic villain, but a label born of scientific frustration, pointing to a pattern in the very first light of creation that should not, by all our theories, be there. To understand it, we must look at the cosmic microwave background, the CMB. This is the afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old, a faint microwave whisper that permeates all of space. When scientists created exquisitely detailed maps of this ancient light, like the ones from the Planck satellite, they expected to see a beautiful, random tapestry of hot and cold spots. The cosmological principle, a cornerstone of modern science, insists that the universe is homogeneous and isotropic. In simpler terms, on the largest scales, it should look the same in every direction with no special place and no preferred axis. The maps, however, revealed a subtle but shocking pattern. The fluctuations in temperature, those tiny variations from the average, are not completely random. They appear to have a faint alignment, a preferred direction that seems to correlate with the plane of our own solar system and the motion of our sun through the galaxy. It is as if the blueprint of the infant universe is subtly tilted toward our local neighborhood. The implications of this, if it is real and not some colossal statistical fluke, are staggering. It could mean one of two deeply troubling things. First, it might suggest that our solar system occupies a privileged central place in the cosmos, a throwback to pre-Copernican thinking that modern science utterly rejects. The second, and more likely possibility to scientists, is even more disturbing. It could indicate a fundamental flaw in our understanding of the universe's structure from its very first moments. Perhaps the seeds of cosmic structure were not sown randomly, but were imprinted with a directional preference that has persisted for over 13 billion years. Skeptics argue vigorously that this alignment is a trick of perception, a systematic error in how we subtract the foreground glow of our own galaxy, or simply an unlikely but possible random pattern in the data. Yet, despite years of analysis and increasingly precise measurements, this eerie signal has not gone away. The axis of evil stands as a quiet, persistent whisper in the oldest light we can see, a whisper that suggests the universe might have a tilt, a preferred direction, and that we are somehow disconcertingly aligned with it. The unsettling alignment of the axis of evil is written in the oldest light, but a more recent visitor brought its own mystery right to our cosmic doorstep. In October 2017, astronomers at the Pan-STARRS telescope in Hawaii spotted a faint point of light moving at impossible speed. This was not an asteroid from our solar system. Its trajectory was hyperbolic, meaning it was not bound by the sun's gravity. It was a traveler from another star, the first interstellar object ever detected passing through our neighborhood. They named it Oumuamua, a Hawaiian word meaning scout or messenger from the distant past. As telescopes around the world swiveled to observe it, the data revealed a shape unlike anything in our own solar system. Based on how its brightness changed dramatically as it tumbled, scientists deduced it was highly elongated, perhaps 10 times as long as it was wide. Some described it as a cigar, others as a pancake. This was strange, as most asteroids and comets are more lumpy or spherical. Then came the second and more profound anomaly. As Oumuamua swung around the Sun and began its journey back into interstellar space, it did something inexplicable. It sped up. Its trajectory could not be explained by gravity alone. It was experiencing a non-gravitational acceleration, as if it had a gentle but persistent push from within. Comets do this when their ices heat up and vent gas, creating a jet-like effect. But Oumuamua showed no visible coma, no cloud of gas and dust, no tail. It was dark, reddish, and utterly dry in appearance. The scientific community scrambled for explanations. Could it be a solid hydrogen iceberg, slowly evaporating in the sun's warmth and providing thrust with invisible gas? Or a chunk of frozen nitrogen, like a piece of a distant Pluto-like world? These exotic ideas were proposed because common ices like water would have produced a visible coma that was never seen. The most provocative hypothesis came from Harvard astronomer Avi Loeb, who suggested its unusual shape and acceleration were consistent with a thin, lightweight object pushed by sunlight itself, a fragment of a broken light sail, an artifact of alien technology. While most scientists favor a natural origin, the complete lack of a definitive answer, the perfect storm of its strange shape, its silent acceleration, and its fleeting visit before it vanished forever, has cemented Oumuamua as a permanent cosmic riddle. Its story, however, was given a crucial counterpoint just 2 years later. In August 2019, an amateur astronomer named Gennady Borisov in Crimea spotted a second visitor. This object, named 2I Borisov, was everything Oumuamua was not. As it approached the Sun, it developed a brilliant, fuzzy coma and a distinct tail. Spectroscopic analysis showed it was outgassing cyanogen and diatomic carbon, classic signatures of a comet. It looked and behaved exactly like a comet from our own solar system, just one that was born around another star. The stark contrast between these two visitors is what makes Oumuamua so haunting. Borisov was a familiar face from an unfamiliar place, proving that interstellar space is littered with ordinary icy material. Oumuamua was the true oddity, the one-of-a-kind object that passed through our backyard, displayed a handful of impossible traits, and left without ever revealing what it truly was. It remains a silent messenger, its secrets forever locked in its journey between the stars. Oumuamua's strange journey highlights the oddities that pass through our cosmic neighborhood, but some anomalies are not visitors, they are permanent, terrifying absences. Deep in the constellation of Bootes the Herdsman lies a region of space so profoundly empty it has earned the name the Great Void. This is not just a sparse patch, it is a spherical chasm in the cosmic web, a bubble of near-nothingness stretching an almost incomprehensible 330 million light-years across. To grasp that scale, consider our own Milky Way galaxy is a mere 100,000 light-years wide. You could fit thousands of galaxies like ours across this void, yet you would find almost none. In a universe where matter is clustered into a vast, frothy network of filaments and walls, the Bootes void is a staggering hole, a cosmic desert of unprecedented size. Its discovery in the 1980s sent shockwaves through cosmology. When astronomers like Robert Kirshner were mapping the large-scale structure of the universe, they expected a relatively even distribution, a cosmic foam. Finding a void this vast was like surveying a sprawling metropolis from the air and discovering a perfectly circular region the size of a continent containing only a handful of isolated houses. It directly challenges our models of how the universe evolved after the Big Bang. The subtle fluctuations in the early universe should have led to a web-like structure, but they should not have left gaps this monstrous. According to standard theory, a void of this scale is statistically so unlikely it borders on the impossible. It is a great cosmic should not be here. Yet it is not completely barren. Painstaking surveys have located a sprinkling of galaxies within this immense darkness, perhaps 60 in total, where thousands should exist. These lonely island universes, like the spiral galaxy MCG plus 053330, only deepen the mystery. They are not clustered together, but scattered like a few lost stars in an endless night. Their very existence is a puzzle. Did they form in this desolation against all odds? Or are they the survivors of a region that was once richer, now left behind as the void expanded? The leading theory to explain the void's existence is as fascinating as the void itself. It may be the result of a cosmic merger. Imagine several smaller voids like soap bubbles coalescing over billions of years. Their walls would thin and pop, their interiors joining to create one colossal empty region. This could explain the scale, but it remains a hypothesis. The Bootes void stands as a monument to our incomplete understanding, a silent, spherical question mark in the cosmos that forces us to wonder what other vast nothings might lie in the darkness, waiting to be found. While the Bootes void is a staggering emptiness, another anomaly is said to lurk much closer to home, woven from shadow, radio waves, and a deep human desire for hidden truths. This is the legend of the Black Knight satellite. The story begins not in the space age, but in the late 19th century with the brilliant, enigmatic inventor Nikola Tesla. In 1899, while experimenting with his high-voltage apparatus in Colorado Springs, Tesla reported picking up strange, rhythmic radio signals. He believed they might be attempts at communication from another world, perhaps Mars. Decades later, in the 1920s, amateur radio operators began reporting odd echoes where their own signals seemed to return to them seconds after transmission, as if bounced off something unknown in orbit. These early, unexplained whispers formed the first threads of the myth. The tale truly crystallized in 1954, when newspapers reported that the United States Air Force had detected two mysterious satellites orbiting Earth at a time when no nation had yet launched one. This report, though later attributed to misidentified natural objects, planted a powerful seed, the idea of an ancient watchtower circling our planet. The legend gained its most iconic visual evidence in 1998. During the Space Shuttle Endeavour's STS-88 mission, which was assembling the International Space Station, astronauts photographed a strange, angular black object against the backdrop of Earth. The image, released publicly, went viral in the early Internet age. It appeared to show a crafted, asymmetrical piece of technology, not a natural rock. For believers, this was the ultimate proof, a photograph of the Black Knight taken by NASA itself. The reality, however, is a masterclass in how mysteries are built from layers of misunderstanding. The 1998 photograph almost certainly shows a thermal blanket, a piece of multilayered insulation that had been lost during an earlier spacewalk. The blanket, tumbling slowly in the zero gravity, took on a rigid, angular appearance as its layers expanded in the sunlight. As for the earlier signals, Tesla was likely detecting natural radio pulses from celestial bodies like Jupiter, while the delayed radio echoes were probably caused by unusual atmospheric conditions. The 1954 satellite report was likely tracking pieces of debris from earlier, secret rocket tests or misinterpreting astronomical phenomena. Yet the persistence of the Black Knight story is more fascinating than any debunking. It taps into a profound and timeless narrative, the suspicion that we are not alone and that those in power are keeping the truth from us. It transforms a lost piece of foil into an artifact of impossible antiquity, a silent sentinel that has watched over human civilization for millennia. The Black Knight is not a physical object but a cultural one, a modern myth born from our collision with the cosmos, a symbol of the secrets we believe must be hiding in the vast, silent dark above us. The myths we create about hidden satellites speak to our longing for cosmic company, but sometimes the most perplexing signals come not from legends, but from our own trusted robotic explorers. For decades, two pioneering spacecraft sent a quiet, persistent whisper back to Earth that no one could decipher. The Pioneer 10 and Pioneer 11 probes, after completing their historic flybys of Jupiter and Saturn, were on trajectories to become the first human-made objects to leave our solar system. As they sailed into the dark, engineers meticulously tracked their positions using the Doppler shift of their radio signals. By the early 1990s, a tiny, nagging discrepancy emerged in the data. Both spacecraft, now billions of miles from the Sun, were slowing down just a little bit more than they should have been. It was a minuscule, constant deceleration, a sunward tug equivalent to just 10 billion times weaker than the gravity we feel on Earth. To put it in human terms, it was like the probes were being held back by a force equal to the weight of a single grain of sand. Yet, this tiny anomaly was utterly real, and it persisted year after year, accumulating into a deviation of hundreds of thousands of miles from their predicted path. This was the Pioneer anomaly, and it defied every conventional explanation. Scientists considered and rejected countless possibilities. Was it the gravitational pull of unknown dark matter in the solar system? Was it a subtle error in our understanding of gravity itself? A hint that Einstein's theory of general relativity needed a tweak at the vast scales of interplanetary space. For over 20 years, the anomaly remained a thorn in the side of physics, a whisper from the void suggesting our maps of reality were incomplete. The solution, when it finally came, was a masterpiece of meticulous, painstaking science. A dedicated international team spent years recovering old telemetry data, building precise computer models of the spacecraft down to the last bolt and wire, and accounting for every conceivable force. The culprit they discovered was not new physics, but an exquisitely subtle thermal effect. The Pioneer probes were powered by radioisotope thermoelectric generators, essentially nuclear batteries that produced heat and converted it to electricity. That heat had to go somewhere. The team's models revealed that this heat was not radiating away from the spacecraft uniformly. Slightly more thermal radiation was escaping from the back of the dish-shaped antenna, which faced toward the Sun, than from the front. This anisotropic or directionally uneven radiation acted like a tiny photon rocket. Each infrared photon carrying heat away from the spacecraft also carried a minuscule amount of momentum. Because a little more momentum was being pushed out the back, it created a net thrust, ever so gently pushing the spacecraft back toward the Sun. It was the spacecraft's own warmth, slowly bleeding into space, that had been breaking their journey all along. The resolution of the pioneer anomaly is a profound lesson in the scientific process. It began as a thrilling mystery that hinted at revolutionary physics lurking in the dark. It ended not with a bang, but with a careful accounting of heat from a nuclear battery. Yet that journey was anything but mundane. It forced engineers and physicists to examine the universe and our own technology with unprecedented precision. It showed that even when the answer is conventional, the pursuit of an anomaly can drive us to new levels of understanding, refining our instruments and our models for the next truly unexplained mystery that awaits in the deep. The precise geometry of the Red Rectangle Nebula shows how stars can sculpt their surroundings, but the star we call Tabby's star performs its mysteries on a vastly longer and more erratic timeline. Beyond its famous, sharp drops in brightness lies an even more perplexing behavior, a slow, relentless fading that has unfolded over more than a century. While telescopes like Kepler caught the star in the act of its dramatic, day-long dimming events, astronomers turned to a much older archive to uncover this deeper secret, the Harvard College Observatory's collection of photographic glass plates. These plates, painstakingly exposed by astronomers for over 100 years starting in the 1890s, contain a continuous record of the northern sky. By digitizing and analyzing the faint images of Tabby's star on these historic plates, researchers made a staggering discovery. The star has been dimming almost imperceptibly year by year for the entire duration of the record. This is not a short-term fluctuation or an instrumental glitch. The dimming is consistent across different telescopes and photographic emulsions, ruling out errors. The total drop is profound. The star has faded by roughly 20% over the course of a century. This secular dimming presents a monumental new layer to the puzzle. The sharp, irregular dips we discussed earlier are like sudden, violent tremors, but this long-term fade is the slow sinking of the entire continent. Any viable theory must now explain both phenomena simultaneously, a challenge that has strained our models of stellar behavior to their limits. The most accepted framework involves dust, but of a very specific and strange kind. To cause the long, gradual dimming, a vast, uneven cloud of fine circumstellar dust must be orbiting the star, perhaps in a giant, lopsided ring or a swarm of countless fragments. This cloud would need to be optically thin, meaning it doesn't completely block the light but subtly filters it, scattering blue wavelengths more effectively and giving the star a redder appearance, which is indeed observed. The sharp, deep dips could then be caused by denser clumps within this cloud, or by the transits of larger, disintegrating planetary bodies trailing immense shrouds of debris. Yet the perfect model remains elusive. A simple dust cloud should also produce an excess of infrared radiation, as the dust grains absorb starlight and re-emit it as heat. While some infrared excess has been detected, it is not as strong as many models predict. Furthermore, the dust would need to be incredibly fine, smaller than particles in cigarette smoke, to explain the light-scattering properties, and such tiny grains should be blown away by stellar radiation pressure on short timescales. This implies the cloud must be continuously replenished by some catastrophic and ongoing process, like the grinding collision of moons or the slow evaporation of a giant comet swarm. The long-term dimming of Tabby's star transforms it from a curious oddity into a deep cosmic clock, ticking down over generations. It forces us to consider stellar histories we have never witnessed, where a star can be slowly, patiently shrouded by the ruins of its own system, a process so gradual it writes its story not in years but in centuries of fading light. The slow, patient dimming of a star is a story written over eons, but our own galaxy tells a far more violent tale, one of cosmic consumption and stellar catapults. This is the reality of galactic cannibalism, a process as brutal as it sounds, where larger galaxies, driven by immense gravity, literally tear apart and devour their smaller neighbors. Our Milky Way is not a serene island universe, it is a predator, and its current meal is the Sagittarius dwarf elliptical galaxy. This tiny satellite galaxy, containing perhaps only a few 100 million stars, has been orbiting the Milky Way for billions of years. With each close pass, our galaxy's overwhelming tidal forces, the difference in gravity between the near side and far side of the dwarf, stretch and shred it, pulling out long, shimmering streams of stars that wrap around our galactic halo like celestial ribbons. These stellar streams, ghostly remnants of a galaxy being dismantled, are visible to telescopes as faint rivers of light arcing across the sky. The Sagittarius dwarf is now on its death spiral, having passed through the plane of the Milky Way multiple times, each passage stripping away more of its stars and gas, which are now being assimilated into the larger galaxy. This process is not unique to us. It is how all large galaxies grow, a hierarchical merging that builds giants from the pieces of countless dwarfs. But from this destructive feast comes an astonishing byproduct, the creation of hypervelocity stars. These are not merely fast stars, they are galactic projectiles, solitary suns hurtling through space at speeds exceeding 1 million miles per hour, so fast they are on a one-way trip out of the Milky Way entirely. Their origin story is a cosmic slingshot, a gravitational maneuver of breathtaking precision and violence. It begins in the crowded core of our galaxy, near the supermassive black hole Sagittarius, a star. When a binary star system, two stars orbiting each other, wanders too close to this gravitational monster, a catastrophic dance unfolds. The black hole's immense gravity can capture one star while violently ejecting its companion. It is a gravitational three-body interaction of immense power. As one star is pulled into a tight orbit around the black hole, the other is flung away at a staggering fraction of the speed of light, like a stone from a sling. This ejected star then rockets through the galaxy, its velocity so great it overcomes the Milky Way's collective gravitational pull. The first of these renegade stars was discovered in 2005, a massive blue star speeding away from the galactic center at over 1.5 million miles per hour. Since then, dozens more have been identified, some even appearing to originate from other galaxies, suggesting this violent process is universal. These hypervelocity stars are more than just curiosities. They are direct evidence, forensic clues of the violent events happening in galactic cores. Each one is a living tracer bullet, its trajectory pointing back to the scene of the crime, the chaotic region around a supermassive black hole. They serve as permanent records of galactic cannibalism and the titanic forces that shape our universe, proving that from the act of destruction comes the birth of the fastest solitary travelers in the cosmos. These stellar catapults, born from galactic violence, travel through a universe filled with structures of immense scale and light. But not all galaxies blaze with the fierce glow of billions of suns. Some are cosmic phantoms, vast yet almost invisible, drifting through the darkness like ships made of mist. These are the ultra-diffuse galaxies, and they represent one of the most perplexing anomalies in modern astronomy. Imagine a galaxy the size of our own Milky Way, with its majestic spiral arms spanning 100,000 light-years. Now take away 99% of its stars. What remains is an ultra-diffuse galaxy, a ghostly expanse so faint that its light is spread thinner than a wisp of smoke against the black velvet of space. For decades, these objects simply slipped through our nets. Their surface brightness is so low that they blend seamlessly into the background glow of the night sky, invisible to traditional surveys that hunt for concentrated points of light. Their discovery required a perfect storm of technology and patience. It was within the dense, chaotic environments of massive galaxy clusters, like the Coma cluster and the Virgo cluster, that astronomers finally began to see them. Using ultra-sensitive instruments on telescopes like the Subaru Observatory and the Dragonfly telephoto array, a custom-built instrument that uses commercial camera lenses to minimize scattered light, researchers began to pick up these enormous, smudgy patches. They were not small, faint dwarfs. They were giants, but giants made of almost nothing. This presents a profound physical puzzle. A structure that large with so few stars has very little gravitational pull from its visible matter. According to the laws of motion, such a sparse collection of stars should simply fly apart. The galaxy's own rotation, or even the gentle tidal tug from neighboring galaxies in a cluster, should tear it to shreds. Yet, these ultra-diffuse galaxies are not flying apart. They hold their shape, enduring for billions of years in the most gravitationally violent neighborhoods in the universe. The only plausible explanation points to the invisible hand of dark matter. The leading theory is that these are failed galaxies. In the early universe, a vast halo of dark matter began to collapse, its gravity pulling in gas to form stars. But in these particular cases, something went wrong. Perhaps the gas was stripped away by the hot intergalactic medium of a cluster before many stars could form, or maybe star formation was incredibly inefficient. The result is a galaxy-sized dark matter halo that, for reasons we do not fully understand, failed to light up. The dark matter provides the gravitational skeleton, the hidden mass that holds the scant population of stars in place, preventing them from scattering into the void. This makes ultra-diffuse galaxies perhaps the purest dark matter laboratories we have ever found. In a normal galaxy like the Milky Way, the gravitational signal is a complex mix of stars, gas, and dark matter, making it hard to isolate the dark matter's properties. But in an ultra-diffuse galaxy, the visible matter is so minimal that its gravity is almost negligible. The dynamics of the galaxy, how its few stars move, are dominated almost entirely by the dark matter halo. By studying these ghosts, astronomers can map the distribution of dark matter with unprecedented clarity, testing our models of how this mysterious substance behaves. They are cosmic silhouettes where the absence of light reveals the shape of the invisible. Ghostly galaxies are defined by their near silence, but the cosmos also speaks in sudden, deafening shouts. Among the most energetic and bewildering signals ever detected are fast radio bursts, or FRB. These are not gentle whispers but cosmic fireworks, fleeting explosions of radio waves that pour more energy into the sky in a single millisecond than our sun emits in 80 years. For that brief, brilliant flash, an FRB outshines entire galaxies in the radio spectrum, then vanishes without a trace. Their story begins not with a live observation, but with a detective digging through old data. In 2007, astronomer Duncan Lorimer and his student David Narkevic were analyzing archival recordings from the Parkes Radio Telescope in Australia, searching for distant pulsars. Buried in observations from 2001, they found something astonishing, a spike of radio energy so powerful it saturated the telescope's receiver. It lasted just 5 milliseconds and appeared to come from deep intergalactic space. This event, now known as the Lorimer burst, was so extreme that many in the scientific community were deeply skeptical. Could it be a glitch, a satellite's reflection, or even a microwave oven being opened prematurely in the observatory's kitchen? The signal seemed too good to be true, a lone anomaly without a clear explanation. But Lorimer's burst was not a fluke. As radio telescopes became more sensitive and survey projects began scanning the sky continuously, more of these bursts were found. The true revolution came in 2016, when astronomers discovered an FRB that repeated. Unlike the one-off Lorimer burst, this source, designated FRB 121102, flashed again and again. This single fact ruled out cataclysmic, one-time events like the collision of two neutron stars or the death of a star, because you cannot have the same explosion happen multiple times. The repeater allowed scientists to do something previously impossible, to pinpoint its home. Using a network of telescopes across the globe, they traced its origin to a small, faint dwarf galaxy over 3 billion light-years away. Since then, dozens of repeaters and many one-off bursts have been localized to a variety of host galaxies, confirming they are genuine, extragalactic phenomena of immense power. So what cosmic engine can produce such a staggering, fleeting blast? The leading suspect for the repeating bursts is a type of stellar corpse called a magnetar. These are neutron stars with magnetic fields 1,000 trillion times stronger than Earth's, the most powerful magnets in the universe. Theorists suggest that a starquake on the surface of a magnetar, a sudden cracking of its rigid crust under immense magnetic stress, could release a titanic wave of energy that we see as an FRB. For the non-repeating, one-off bursts, the source could be more violent, perhaps the final merger of two neutron stars or the collapse of an extremely massive star into a black hole. Yet many mysteries remain. Why do some sources repeat while others do not? What precise mechanism on a magnetar can channel such focused energy? Could there be multiple types of sources creating similar signals? Each new detection adds a piece to the puzzle, but the full picture of these millisecond cosmic sirens, first glimpsed in a skeptical review of old data, remains one of the most active and thrilling frontiers in modern astrophysics. The fleeting brilliance of cosmic radio bursts exists on a scale we can scarcely fathom, but within our own solar system, a different kind of anomaly has been spinning with perfect geometric patience for decades. At the north pole of the planet Saturn, a storm of breathtaking precision rages, a hexagon of clouds so vast it could swallow 4 Earths whole. This is not a trick of light or a fleeting atmospheric quirk. It is a permanent fixture, a 6-sided jet stream that has maintained its shape since we first glimpsed it in the 1980s. The Voyager spacecraft first spotted the faint outline of this bizarre structure, a hint of something impossible at Saturn's cloud-shrouded pole. But it was the Cassini orbiter arriving in 2004 that revealed the hexagon in all its terrifying glory. For over 13 years, Cassini's cameras watched as this colossal polygon, each side longer than the diameter of our planet, rotated with the planet's deep rhythm, unchanging through seasons that last for years. The hexagon is a standing wave pattern, a kind of atmospheric oscillation frozen in place. Imagine blowing air across the top of a soda bottle to create a musical note. The hexagon is like that note but played on a planetary scale. It is formed by a high-speed jet stream, a river of air screaming eastward at over 200 miles per hour that wraps around Saturn's pole. Where this jet stream interacts with the slower-moving atmosphere beneath it, a stable wave pattern emerges, pinning the clouds into this angular shape. The mystery is not that waves can form in a rotating fluid, but why they lock into a hexagon, and why that hexagon is so absurdly durable. Laboratory experiments here on Earth provide a crucial clue. When scientists spin a cylinder of fluid simulating a planet's polar region, they can create similar polygonal shapes, including squares, triangles, and hexagons. The shape that forms depends on the speed of the rotation and the differences in velocity between layers of the fluid. Saturn's specific combination of spin and atmospheric shear seems to favor a 6-sided pattern. Yet the laboratory versions are fleeting and small-scale. Saturn's hexagon is a planetary tattoo, etched into the atmosphere for what may be centuries. What precise cocktail of wind speeds, temperature gradients, and planetary density keeps this pattern so perfectly stable while everything else in the solar system's weather is chaotic and shifting? The hexagon also has a depth that defies simple explanation. Cassini's instruments revealed that this geometric storm plunges hundreds of miles down into the atmosphere, a structure with deep roots. Furthermore, its color changes with Saturn's long seasons, shifting from a bluish hue to a golden brown as sunlight returns to the North Pole, suggesting complex chemistry at play within its boundaries. This persistence is what makes it such a profound anomaly. Hurricanes on Earth dissipate in days. The great red spot of Jupiter, while centuries old, is a swirling oval, a shape we expect from turbulent fluids. The Saturn hexagon is a rigid geometric form imposed on a chaotic gaseous giant, a natural pattern so perfect it looks engineered. It stands as a humbling reminder that the physics of fluid dynamics, even in our own celestial backyard, can produce wonders we are only beginning to decode. The rigid geometry of Saturn's hexagon is a product of its own atmosphere, but some of the most energetic particles in the universe travel from unimaginable distances, only to be stopped by the faintest whisper of ancient light. This is the mystery of the GZK cutoff, named for the physicists Grison, Zatsepin, and Kuzmin. Their theory, formulated in the 1960s, describes a fundamental speed limit for cosmic rays traveling across the vastness of intergalactic space. Cosmic rays are not rays of light. They are atomic nuclei, protons, or the cores of heavier elements hurtling through the void at nearly the speed of light. The most energetic of these particles carry as much kinetic energy as a professionally thrown baseball, all packed into a single subatomic speck. According to the GZK theory, such a particle, on its billion light-year journey from a distant galaxy, should not be able to reach us. The reason is the cosmic microwave background, that same ancient afterglow we discussed earlier. While it is incredibly cold and faint, it fills every cubic inch of the universe. An ultra-high-energy proton screaming through this bath of microwave photons will inevitably collide with them. These are not gentle nudges. Because the proton is moving so incredibly fast, it sees the low-energy microwave photons as high-energy gamma rays due to the relativistic Doppler effect. When they collide, they produce new particles, specifically pions. This process saps the proton's energy, like a marathon runner constantly having to push through a dense, invisible fog. Over distances greater than about 150 million light-years, the theory states any proton with energy above a certain threshold around 5 times 10 to the 19th electron volts should be slowed down below that limit. It should be cut off. This creates a cosmic horizon for the most energetic particles. We should only see ultra-high-energy cosmic rays that come from relatively nearby sources within our local galactic neighborhood. The paradox arrived with the data. Giant observatories like the Pierre Auger Observatory in Argentina and the Telescope Array in Utah have indeed detected these particles, these cosmic baseballs raining down on our atmosphere. They create massive air showers, cascades of secondary particles that spread over miles. The measurements are unambiguous. The energies are far above the GZK cutoff. This presents a thrilling puzzle. If the GZK theory is correct and our understanding of particle physics and the cosmic microwave background suggests it is, then these ultra-high-energy cosmic rays must be coming from sources within a few hundred million light-years of Earth, a relatively small volume in the cosmic scheme of things. So where are these nearby cosmic accelerators? What natural engine can take a single atomic nucleus and fling it across space with a force 100 million times greater than the most powerful particle collider we can build? The suspects are suitably dramatic. One prime candidate is the active galactic nucleus, the furious core of a galaxy powered by a supermassive black hole feeding on vast amounts of matter. The relativistic jet screaming from its poles could, in theory, accelerate particles to these energies. Another possibility is the aftermath of a gamma-ray burst, the most violent explosion in the universe since the Big Bang, which could create a shock wave of unbelievable power. Yet, when astronomers trace the rough arrival directions of these mysterious cosmic rays back into the sky, they find no obvious, brilliant source staring back at them. No nearby quasar or recent cataclysm lines up perfectly. The search is like trying to find a specific gun that fired a bullet in a crowded city during a hurricane, when you only have a vague sense of the neighborhood it came from. The particles are electrically charged, so their paths are bent and twisted by the magnetic fields that weave through intergalactic space, obscuring their true origins. The GZK paradox therefore stands at a fascinating crossroads. It may be guiding us to a new class of hidden cosmic powerhouses in our intergalactic backyard, or it might be hinting at a subtle flaw in our understanding of how matter interacts with the oldest light in the universe. Each detection is a messenger from a nearby cosmic catastrophe, carrying a coded address we are still struggling to read. The cosmic rays that smash into our atmosphere carry messages from nearby violence, but the universe holds a deeper, more intimate connection that defies our every intuition about distance and separation. This is the phenomenon of quantum entanglement, often called spooky action at a distance, a phrase coined by a deeply skeptical Albert Einstein. At its heart, entanglement is a link forged between two particles like photons or electrons that have interacted. Once entangled, their fates become intertwined no matter how far apart they are sent. Measure a property of one, like its spin or polarization, and the other instantly assumes a corresponding state. This instantaneity is the spookiness. It suggests an influence traveling faster than light, a direct violation of the cosmic speed limit Einstein himself established. For decades, physicists debated whether this was a real connection or just a sign of hidden variables, unknown factors predetermined at the moment of entanglement. The pivotal moment came with experiments by scientists like John Bell, whose tests provided a way to distinguish between local hidden variable theories and the stranger reality of quantum mechanics. The results have been decisive time and again, confirming that the spooky connection is real. The particles do not simply contain hidden instructions, they are genuinely linked in a way that transcends space. This has been tested over ever greater distances, from labs across university campuses to fiber optic links under cities spanning hundreds of miles. The current frontier pushes this into the cosmos itself, with proposals and early tests using satellites to entangle photons and beam them to ground stations separated by thousands of miles. The goal is to see if this quantum bond holds across the vast, empty expanse of Earth's orbit, creating an unbreakable, instantaneous link between continents. If it does, and all evidence suggests it will, the implications shake the foundations of reality. It challenges the classical notion of locality, the idea that objects are only influenced by their immediate surroundings. Instead, it paints a picture of a universe where, at a fundamental level, separation may be an illusion. The particles are not communicating. There is no information transfer we can exploit to send a message faster than light. Rather, they behave as a single, non-local entity. This forces a profound philosophical question. If two particles separated by the width of a galaxy can remain an interconnected whole, what does that say about the fabric of the cosmos? Could the universe itself be born from a state of total entanglement, a primal connection that has subtly woven itself into the structure of everything we see? The spooky action Einstein rejected may not be a mere particle trick, but a fundamental feature of reality, hinting that the universe is far more deeply and strangely interconnected than our classical minds can comfortably grasp. Quantum entanglement suggests a universe woven together by invisible threads, but when we try to take a simple inventory of the cosmos, we run into a startling accounting error. For all the talk of dark matter and dark energy, there is a fundamental mystery about the very stuff we are made of. This is the missing baryon problem. Baryons are the particles of ordinary matter, the protons and neutrons that form atoms, stars, planets, and us. Based on precise measurements of the cosmic microwave background, the blueprint of the infant universe, we know exactly how much of this ordinary matter should have been created in the Big Bang. The math is clear and elegant, yet when astronomers tally up all the visible baryons in the present-day universe, every star in every galaxy, every wisp of gas in every nebula, every planet and piece of dust we can detect, they come up shockingly short. We can only account for roughly half of the ordinary matter that our theories insist must exist. It is as if you carefully counted every ingredient going into a vast recipe, but when you looked at the final dish, half the flour had simply vanished. The question is not trivial. It is a direct challenge to our understanding of cosmic evolution. Where did 50% of the atoms in the universe go? The leading suspect is not in some distant, hidden dimension, but all around us in the vast, empty spaces between galaxies. Theorists believe the missing baryons are floating in a diffuse, superheated gas known as the warm-hot intergalactic medium, or the WIM. This is not a cloud you could see. It is a ghostly web of matter, 1,000,000 times less dense than the air we breathe, but heated to temperatures of hundreds of thousands, even millions of degrees. At such heat, the gas is ionized, meaning its electrons have been stripped from their atoms, making it completely invisible to optical telescopes. It permeates the cosmic web, the filamentary structure of the universe, tracing the lines where galaxies cluster like dew on a spider's silk. Detecting this ethereal medium is one of the great observational challenges in modern astronomy. Because it is so hot and thin, it does not emit much light of its own. Instead, scientists hunt for its shadow. They use the brightest beacons in the distant universe, quasars, as cosmic flashlights. As the intense light from a quasar travels billions of light years to reach us, it passes through these filaments of the WIM. The superheated gas absorbs specific wavelengths of that light, leaving faint, telltale dips in the quasar's spectrum, like fingerprints from particular elements such as oxygen and neon. It is painstaking work, requiring the most sensitive space telescopes, like the Chandra X-ray Observatory and XMM Newton, to catch these whispers of absorption. Slowly, piece by piece, evidence is mounting that the WIM is real and contains a significant portion of the missing mass. Yet, fully mapping this hot, diffuse cosmic web and confirming it holds all the lost baryons remains a monumental task. The missing baryon problem forces us to confront a humbling reality. We do not even have a complete census of the familiar atoms that build our reality. The universe has hidden half of its ordinary matter in plain sight, in a form so subtle it took us decades to even begin to see its shadow. This hunt for the universe's missing atoms takes place in a vast, invisible web, but sometimes the cosmos reveals its violence with spectacular clarity. A streak of blue light, over 200,000 light-years long, arcs across the darkness like a celestial scar. At its tip, a point of unimaginable gravity, a supermassive black hole with the mass of 20 million suns, is not sitting quietly at the center of a galaxy. It is running. This rogue behemoth, discovered by the Hubble Space Telescope, is racing through intergalactic space at a staggering speed, perhaps 4 million miles per hour, fast enough to travel from Earth to the Moon in under 15 minutes. It is not traveling alone. In its furious wake, it has left a contrail of shocked gas and, astonishingly, newborn stars. The black hole is plowing through the dense gas that floats between galaxies like a ship through a cosmic sea. The force of its passage compresses this gas, triggering the collapse of stellar nurseries and igniting a linear firestorm of star formation. This brilliant trail is the evidence, a smoking gun pointing back to a cataclysm of almost unimaginable scale. The leading theory for its origin is a galactic game of gravitational billiards involving 3 players. Imagine 2 galaxies merging, each with its own central supermassive black hole. These black holes would begin to orbit each other, sinking toward the new galaxy's core through a complex dance. If a third galaxy with its own black hole then joined this chaotic merger, the 3-body gravitational interaction could become violently unstable. In this cosmic slingshot, one of the black holes could be flung out of the galactic core at tremendous speed, while the other 2 would recoil in the opposite direction, likely merging into a single, more massive object. This is precisely what astronomers believe happened. The runaway black hole we see is the ejected projectile, a Titan cast adrift. The evidence is compellingly clear. At the leading tip of the brilliant star trail, Hubble found a compact, bright knot of ionized gas with all the signatures of a black hole's accretion disk, yet no surrounding galaxy. At the opposite end of the trail lies a disturbed galaxy with a bright, active nucleus, the likely recoiling merger remnant. Between them stretches that impossibly long, straight line of young blue stars and glowing gas, a path of destruction and creation forged in a single, violent instant. This discovery shatters the quiet assumption that supermassive black holes are forever anchored to the hearts of their galaxies. It proves they can be evicted, sent careening into the void. This opens a terrifying and thrilling possibility. How many more of these dark giants are wandering unseen through the immense spaces between the galaxies? They would be nearly impossible to detect unless, like this one, they were caught in the act of plowing through a gas cloud and lighting their way. Each rogue black hole is a monument to the most violent events in the universe, the mergers of galaxies, events that can literally catapult the most destructive objects in existence out into the cosmic darkness forever alone. That rogue black hole, a cosmic castaway, reveals the violence of galactic collisions, but the universe holds a deeper, more subtle scar, one imprinted on its very first light. In the map of the cosmic microwave background, the faint afterglow of the Big Bang, there is a region that simply feels wrong. Astronomers call it the CMB cold spot, a vast, circular patch of sky where the ancient radiation is just a little bit colder than the surrounding average. While the CMB is not perfectly uniform, it has a beautiful, speckled tapestry of tiny hot and cold fluctuations. This particular spot is a statistical anomaly. It is far larger and far colder than our standard models of the infant universe predict. The probability of such a feature arising by random chance is extraordinarily low, less than 1 in 200. It stands out like a single, impossibly large and deep footprint on an otherwise gently rippled beach, demanding an explanation. Scientists have proposed two radically different classes of answers, each taking us to the edge of our understanding of cosmology. The first and more conservative explanation involves a staggering emptiness. Imagine light traveling for billions of years across the cosmos. As it passes through regions of space, it feels the subtle tug of gravity from all the matter galaxies, dark matter, gas that lies in its path. If the light enters an area with an average density, it gains a bit of energy falling into that gravitational well and then loses that same amount climbing back out. The net effect is zero, but if the light passes through an immense void, a region where matter is unusually sparse, the story changes. As the light enters this underdensity, it loses energy climbing out of the gravitational well of the denser region it left behind. When it exits the void, it gains less energy falling into the next dense region because the universe has expanded during its journey, weakening the gravitational pull. This net loss of energy, known as the integrated Sachs-Wolf effect, would make the CMB light from that direction appear cooler. So, the cold spot could simply be the shadow of the largest cosmic void we have ever imagined, a so-called supervoid billions of light years across, containing far fewer galaxies than it should. The second explanation is far more speculative and breathtaking. Some theorists suggest the cold spot is not a shadow of a void within our universe, but a bruise from a collision with another universe. In certain models of the multiverse, our cosmos is one bubble in a frothing sea of eternally inflating space, with other bubble universes constantly forming. If, during the universe's violent inflationary infancy, our bubble brushed against a neighboring one, the energy of that collision could have left a distinct circular imprint on the CMB, a region of cooler temperature, exactly like the cold spot. In this scenario, we are not looking at an absence, but at a fingerprint from another reality entirely. The quest to solve this mystery has sent astronomers on a painstaking survey of the distant sky in the direction of the cold spot. They are counting galaxies, trying to map the density of matter to see if a supervoid truly exists there. The results so far are intriguing but inconclusive. Some surveys have found evidence of a large underdensity of galaxies, but its size and emptiness do not seem quite sufficient to explain the profound coldness of the spot. It is like finding a large hole, but one not quite deep enough to cast the shadow we see. Other studies find no significant void at all. This leaves both leading theories in a state of uncertainty. The supervoid explanation is appealing but lacks definitive observational support, while the multiverse collision is a thrilling idea that is, by its very nature, extraordinarily difficult to prove. The cold spot remains a quiet, persistent chill on the map of creation, a cosmic Rorschach test where we see either a monumental nothing or the first tangible evidence of a reality beyond our own. The cosmic cold spot points to a universe of vast emptiness or impossible collisions, but sometimes the most elegant mysteries are not found in the deep sky, but in the gentle glow of our own celestial neighborhood. In the moments just after sunset or before dawn, if you are in a place of perfect darkness, you might see a faint, ethereal triangle of light rising from the horizon along the path of the sun and planets. This is the zodiacal light, a soft, milky pyramid often mistaken for the lingering twilight. For centuries, it was seen as a beautiful but understood phenomenon, sunlight scattering off a vast cloud of fine dust particles that fills the inner solar system, concentrated along the ecliptic plane. This interplanetary dust cloud was thought to be a simple byproduct, the constant grind of asteroids and the evaporating tails of comets leaving a sprinkling of microscopic debris in their wake. It was the solar system's gentle background hum, a settled dust that had been swirling between the planets for eons. Then, a spacecraft on a mission to Jupiter turned its instruments back toward home and heard a different story. The Juno probe, during its journey to the giant planet, carried a sensitive star tracker to help with navigation. As it traveled, it began to detect unexpected, tiny flashes. These were not stars, but impacts, microscopic grains of dust smashing into the spacecraft at tremendous speeds. By mapping the source of these impacting particles, scientists made a startling discovery. The dust cloud was not uniform, and its primary source did not point back to the asteroid belt or a distant comet reservoir. The data strongly suggested the dust was flowing outward from the direction of Mars. This simple observation unravels a long-held assumption. Mars, a small, rocky planet with a thin atmosphere, is now a suspect in a cosmic dust production scheme. How could an entire planet be grinding itself into fine powder and blowing it across the inner solar system? The leading theory points to the Martian moons Phobos and Deimos. These are not spherical worlds, but lumpy, asteroid-like bodies that orbit incredibly close to their planet, especially Phobos. As these moons travel through the stream of interplanetary dust themselves, they are constantly bombarded. When a high-speed dust particle strikes Phobos, it can blast secondary debris off the moon's surface, a process known as impact ejector. Because Phobos orbits so close to Mars and has such weak gravity, this ejected dust can easily escape the moon and be placed into orbit around the sun, slowly spreading out to join the zodiacal cloud. This creates a dynamic new picture where a planet's moons act as giant, ongoing dust mills, their surfaces being sandblasted over millions of years to feed the solar system's dusty ecosystem. The implications challenge our models of planetary science and solar system evolution. It means the zodiacal light is not just a static relic, but an active, dynamic structure, with Mars playing a surprisingly central role in its replenishment. It forces us to reconsider the life cycle of interplanetary dust and how small bodies and their host planets interact in a continuous, grinding dance that literally shapes the light we see in our own night sky. But that beautiful dust born from the grinding of Martian moons traces a solar system we think we understand. At the farthest edge of our vision, however, a fundamental number is coming apart at the seams, threatening to unravel our entire cosmic story. This is the Hubble tension, and it is the most pressing crisis in modern cosmology. The entire narrative of the universe, from the Big Bang to the present day, hinges on one critical number, the Hubble constant. This is the rate at which the universe is expanding, a value that tells us not only how fast galaxies are receding from us, but also how old the cosmos is. For decades, astronomers have refined two supremely precise, independent methods to measure this number. The results should agree, they do not, and the discrepancy is not a small, forgivable error. It is a stubborn, significant gap that has persisted despite ever more careful measurements, suggesting something profound is missing from our model of reality. The first method looks back to the infant universe, to the cosmic microwave background. By analyzing the intricate patterns in this ancient light, the subtle hot and cold spots that are the seeds of all future structure, physicists can deduce the ingredients of the early cosmos, the amounts of dark matter, dark energy, and ordinary matter. Plugging these pristine values into our standard model of cosmology, they can run the cosmic film forward 13.8 billion years and predict what the expansion rate should be today. This early universe method yields a very specific value. The second method measures the universe directly in its present late stage. Astronomers use cosmic lighthouses called Cepheid variable stars and cataclysmic explosions known as Type Ia supernova. Cepheids are stars that pulse with a regularity directly tied to their true brightness. By measuring their pulse rate and how dim they appear from Earth, scientists can calculate their exact distance. Type Ia supernova are even brighter standard candles, exploding with a consistent, known peak brightness. By observing these beacons in relatively nearby galaxies, scientists can build a cosmic distance ladder, step by step, directly measuring how fast those galaxies are moving away from us. This late universe method yields a different, consistently higher value for the expansion rate. The difference is about 10%. 10% may sound small, but in the precise world of cosmology, it is a yawning chasm. It is the difference between a universe that is 13.8 billion years old and one that is significantly younger, a direct contradiction that cannot be brushed aside. This tension means one of two monumental things. Either there is a hidden, systematic error in one of our measurement techniques, a flaw so subtle it has evaded the world's best scientific minds for over a decade. Or, and this is the thrilling possibility, our standard model of cosmology is incomplete. The pristine early universe as seen in the CMB and the messy, evolved universe we see today may be telling different stories because the rules changed somewhere in between. What new physics could bridge this gap? Theorists are exploring breathtaking ideas. Perhaps dark energy, the mysterious force accelerating the expansion, is not constant as we assume. Maybe it evolved over time, growing stronger or weaker in a way that subtly changes the expansion history. There could be a new, unknown type of neutrino or another exotic particle that influenced the early universe's energy density. Some have even suggested more radical revisions to gravity itself. The Hubble tension is not a closed chapter in a textbook, it is a live wire, a frontline mystery being battled in observatories and supercomputers around the globe. It represents a crack in the foundation of our cosmic understanding, and through that crack, we might finally glimpse the true, strange nature of the reality we call home. That profound crack in our cosmic model demands an answer, and the world's top physicists are racing to fill it with brilliant, radical ideas. One leading proposal is called early dark energy. In this scenario, the dark energy we see today driving the accelerated expansion is not a constant force. Instead, it had a powerful, brief surge in the universe's infancy, a sort of cosmic growth spurt just after the Big Bang. This extra push would have subtly altered the conditions imprinted on the cosmic microwave background, the ancient light we use to predict today's expansion rate. If early dark energy existed, it would mean our reading of that baby picture is slightly off, and when we account for that early burst, the predicted expansion rate could align with what we measure nearby. It is a tantalizing fix suggesting the cosmos has multiple gears, an initial violent acceleration that faded, followed by a long coast, and now a reawakening of acceleration in the modern era. Another school of thought looks not to new ingredients but to a rewrite of the fundamental rules. Perhaps Einstein's theory of gravity, general relativity, while spectacularly successful, needs a tweak on the largest cosmic scales. Modified gravity theories propose that the strength of gravity itself has evolved over the lifetime of the universe, or that it behaves differently in the vast, near-empty voids between galaxy clusters than it does in our relatively dense galactic neighborhood. A small change in the law of gravity could recalibrate the cosmic distance ladder or alter how structures formed in the early universe, potentially bridging the gap between the two measurements. It is a monumental proposition challenging a pillar of modern physics, but the tension is severe enough to warrant considering it. A more conservative yet equally profound possibility is that we live in a cosmic bubble. The local universe we use for our late-time measurements, a region a few hundred million light-years across, might be unusually empty, an underdense region or a local void. If our galactic neighborhood has less matter than the cosmic average, the gravitational pull holding galaxies together here would be slightly weaker, allowing them to flow apart a bit faster under the influence of dark energy. This would make our local measurement of the expansion rate appear artificially high compared to the universe-wide average derived from the ancient CMB. We would not be at the center of the universe, but we might be residing in a slightly underpopulated suburb, and our street-level view would be skewed. The path to truth is not through theory alone, but through sharper eyes on the sky. This is where the next generation of cosmic observatories enters the story. The James Webb Space Telescope, with its unparalleled infrared vision, is already revolutionizing the cosmic distance ladder. It can see through dust to observe Cepheid variable stars and Type Ia supernova in galaxies with a clarity Hubble could never achieve, reducing the measurement errors in our local expansion rate. Meanwhile, the upcoming Nancy Grace Roman Space Telescope, set to launch later this decade, will conduct a vast survey of the sky, discovering thousands of distant supernova and mapping the distribution of galaxies and dark matter in 3 dimensions with staggering precision. It will measure the universe's expansion history directly, tracing how the rate changed over billions of years, searching for the fingerprints of early dark energy or a local void. The resolution of the Hubble tension will not come from a single eureka, a moment, but from a global, collaborative siege of data. It is a dynamic, living puzzle at the very heart of cosmology, where every new telescope and every refined calculation brings us closer to knowing whether we need a new particle, a new force, or simply a new map of our own cosmic backyard. The answer will rewrite our story of everything, from the silent, screaming signal to the persistent tension in the very expansion of space. Each of these 25 cosmic anomalies paints a portrait of a universe that is infinitely stranger, more dynamic, and more mysterious than the quiet clockwork we once imagined. These are not mere errors in our data or gaps soon to be filled with simple answers. They are fundamental puzzles, cosmic riddles written in missing matter, impossible geometry, and silent, speeding giants. They remind us that our reality is a story still being written, with chapters we have only begun to decipher. This relentless, wonderful strangeness is not a sign that science is failing. It is the exact opposite. Every unexplained signal, every defiant measurement, every ghostly structure is a beacon. These mysteries are the engines of discovery. They are what push astronomers to build bigger telescopes, physicists to dream bolder theories, and all of us to look deeper into the dark and ask the next great question. They prove that the universe is not a solved puzzle, but an endless frontier of wonder, so we turn the question to you. On this journey through the cosmos's greatest enigmas, which one captured your imagination? Was it the silent, one-time shout of the wow signal, the patient geometric storm at Saturn's pole, or the haunting possibility of a bruise from another universe in the cosmic microwave background? Let us know in the comments below which anomaly you find most compelling and why. And the next time you find yourself under a clear night sky, take a moment to look up. Remember that in that vast darkness between the familiar points of light lie voids that should not exist, stars that flicker with hidden purpose, and forces that defy all explanation. Let that wonder pull you back. If you enjoyed this exploration into the unknown, subscribe for more journeys to the edge of our understanding, where we continue to confront the deepest secrets of the cosmos.